Okay, day 4 with our first unit in Pre-Cal 20, series and sequence. Okay, so we will be looking at the next section, 1.3, which gets us into geometric sequences first. And we're going to break this into two pieces. Excuse me for a minute, I just got to answer something quickly and I'll be right back. Okay, so day 4. Oops. In the sequence and series unit. And we're going to be looking at section 1.3, part 1. Parts to this. We're going to break it into two parts. And we're going to be looking at the geometric sequence. Okay, so obviously we're going to look at the general term formula, look at the definitions. So we're going to define terms. We're going to look at the general formula. Okay, and then we're going to look at some example works and then some practice. And then do some practice. Textbook. Okay, and we're going to break this into two pieces. So this will be part 1 today, and then tomorrow will be part 2, day 5. So let's take a look at what is a geometric sequence. Okay, so it's pretty much fairly similar to what we were doing before, except instead of adding, we're going to multiply now. So a geometric sequence is a sequence where the terms have a common ratio. Where the terms, Okay, so this means basically that we are multiplying between consecutive terms. Multiply, I got to spell. Can't spell today for some reason. Or, here we go. Okay, so that's what a geometric sequence is. So you're multiplying from term to term. So an example of that, so if we started with 4, and then we multiplied by 2 to get 8, and then we multiplied by 2 to get 16, and 32, and 64, and 128, and 256. Okay, there's an example of that. Now you could have negative numbers in there as well. So if I say I started with 3 and I multiplied by negative 2, that would be negative 6. And I multiplied by negative 2, it would be 12. And I multiplied by negative 2, it would be negative 24. And then multiplied by negative 2, that would be 48. Multiplied by negative 2, that'd be negative 96. Okay, so there's a couple examples of how that would work. Okay, you may have also as well, you may multiply by fractions or divide. So say we started with 100 and we multiplied by a half or divided by 2. So we went to 50 and 25. Then 25 over 2, which is 12.5. And then 25 over 4, which is whatever that is, 25 over 8, and so forth, ... And you could have the ... like that as well. So there's examples of geometric sequences. Okay, so how do you get the common ratio? What are the symbols that we're going to use? Let's take a look at defining the symbols next. Okay, so we're going to use R to represent our common ratio. So let me do marker on this. So R is going to be representing our common ratio. And the way that you get the common ratio is you take T2, and you divide by T1, or T3 divided by T2. So 2 consecutive terms in a row where the farthest term, T2 divided by T1 equals R. Or if you like, it could be anything. It could be T5 over T4. Oh, not 4, T4. Right? So it'd be like 8 divided by 4, 16 divided by 8, 132 divided by 64. Okay? And that would give you your common ratio. So in general, it's just one term divided by the other term as you're going. So let's put the T4 in there. Okay, so that's how you get the common ratio. T1 is going to be, again, the first term. Okay, Tn is going to be the general term. Okay, and how do you go about calculating the general term formula? Well, if we had a geometric sequence, okay, we started with T1. The next one would be T1 times R, common ratio. The next one would be T1 times R times R. The next one would be T1 times R times R times R, and so forth and so forth. So you're just raising up R to the next power. So if we were to write that in general term, Tn, the general term, is equal to the first term times R, common ratio, raised to the power of n minus 1, because we have to subtract 1 from the first term. Okay? Okay, and this represents n. Again, we know first term, general term, and of course n is number of terms. Okay, where do you have to be careful? Well, you have to be careful that you don't multiply these two numbers before you raise the R to the power. You have to reuse order of operations. R to the power has to be done first because it's an exponent before you do any other type of calculations using this general form. Okay, so we're going to do a few examples of working through some problems here with the general term. So I'm going to do probably 3 different types of examples today with you, and we'll go from there. So let's cut out and paste the first example that I want to look at today. Let's do this on the next page for examples. Okay, we'll use purple here. Okay. Okay, so I'll kind of do the subscript on these two here, T1 and Tn. Okay, so the first example, type 1, is solving for R, T1, and Tn. Okay, type questions. Okay, so it's 2 people start plant the tree campaign. In the campaign, each person then signs up 3 more people and continues on. What is the common ratio, the first term, and the expression of the general term? Not 2 thous in there. So the general term represents Tn. Okay, so let's put this on subscript. Okay, so first thing we should answer is, okay, what 2 people start a tree planting campaign. So if you're starting with 2 people, that's your first term. So our first term is going to be 2. So T1 is equal to 2 people. Okay, and then it says in the campaign, each person signs up 3 more. So you're going to take 3 more and 3 more and 3 more and 3 more. So if we were to draw this out, if we had one person, then they would go to 3, and then these 3 would go to 3, okay, and so forth and so forth. So you're multiplying out by 3s as you go along here. So it's growing exponentially. Okay? So we can say that the common ratio, what we're multiplying by, we're going from one person to 3, or 2 people to 6 in this case, because one person will get 3 and the other person will get 3. So we know that our common ratio is 3. So we've answered what is the common ratio, what is the first term, and the expression for the general term. So we know that for a sequence, which is geometric, meaning that we're using multiplication, the general term is the first term times r n minus 1. So the general term, we don't know what an n is, so we'll just leave n blank. So we'll say Tn would then equal 2 times r2, which is 3, times n minus 1. So there is our general, and I'm going to put a dot in here so we know that this is multiplied. So this is our general term. Okay. Now when you're working this out, if n is 9, you do 3 to the power of 9 minus 1 before you multiply 2 times 3. You do not ever do that. You always have to do the exponent part first because of order of operations. So don't get confused on that. So there's a very, very simple example for our first one. So let's try an actual calculation one here in our second example. Okay, let's put in here. Okay, a colony starts, this is example 2. A colony starts with 8 members and grows by tripling every year. What is the first 5 terms of the sequence, and find the expression for the general term? So again, we're going to be doing a translation into a term. Okay, so let's start. It starts with 8 members. So if we go into our marker, we know that it's starting with T1 being 8. It grows by tripling every year. So our common multiplication factor, or common ratio, is 3. And what are the first 5 terms of the sequence? Well, we can easily start with 8, multiply it by 3 to get to 24, multiply 24 by 3 to get to 72, multiply 72 by 3 to get to 216, and multiply 216 by 3 to get 648. That gives us our first 5 terms. Okay, fairly easy to do. Start with the first term and then take our common ratio and multiply through. Okay, the other thing that it asks here at the end is find the expression for the general term. So Tn, what is Tn equal to? So we know the formula is T1 times R n minus 1. We don't know what n is. Well, in this case, we could say 5 if we wanted to go that far. But in this case, we're going to do the general term. So we leave Tn blank and we leave n blank. So Tn equals 8 times 3 to the power of n minus 1. There's our general term. Now, this has to be done first before you do any of that multiplying. Remember, order of operations. Sometimes, to avoid confusion, I will even go like this so that people remember to do that first, because sometimes they forget. You don't have to do that, but it does help you, remind you that that has to be done before you multiply the 8. Okay, so that's the general term. Okay, so that's just the first couple examples there were just the same type of example where we're just finding some general term expressions. Okay, so the second type of example that we're going to do, let's do finding a particular term or solving for a particular term. So let's flip our page, and let's cut out this second example types that I've got here on my little bank here over of questions to do. And we'll go and we'll paste it in here. Okay. Example type 2, finding a particular term Tn. Okay. Okay, and I want to put this as a subscript here. Okay, so the radioactive material starts with 5 kilograms of material. After 1 year, there is only 92%. Now, you have to be careful with percent. It's a ratio, but it's not 92. It's 92 over 100. Remember that this symbol, percent, means 92 out of 100. So when you do 92 out of 100, you think of that as 0.92 or 92 over 100. How much will be left after 10 years? Round to the nearest tenth. Okay, so this is finding a Tn. So we have to find out what we know to start. A radioactive material starts with 5 kilograms of material. Now I should put in here that it follows a geometric sequence, because we're not, how do we know that it does or doesn't? But we're going to assume that it does. We should have probably put that in there. So we know that the first term of this sequence is 5 kilograms. And I'm going to put 5.0 because it says round to the nearest tenth. So that'll help me remember. It says after 1 year, there is only 92% left. So that means you're going to be multiplying by 92%, which is 92 over 100. So we know that the common ratio that you're multiplying by is going to be 92 over 100, 92%, or if you like those decimals, 0.92, if we do that. Okay, so there is our common ratio based on the percentage. Okay, and then its n value of this particular says how much will be left after 10 years. So 10 years, the first year it's 5, second year it's something, third year it's something. Okay, so we're going to have 10 years of it sitting there. So let's write our formula out and do some calculation. Okay, our formula is the general term is equal to T1 times Rn minus 1. Okay, so we know that the T10 is what we want. It's going to be after 10 years. Well, the first year it was 5. Okay, and then it was 0.92 to the power of n minus 1, which is 10 minus 1. Okay, so if we do this, it's 5 kilograms, 5.0, times 0.92 to the power of 9. Now, I'm going to put brackets in here so you don't forget. That has to be done before you multiply, otherwise you'll be way off. So you got to take your calculator out, and you can use on your calculator the button to raising to a power button, which on some calculators will look like this, and on other calculators it'll look like this, or y to the x. So on mine it is right there, y to the x. Okay, so what I do is I go 0.92, hit that button, raise to the power of 9, hit the equal sign, I get a decimal number, and I'm not going to round it, and I multiply it by 5. Now, in the question, it says round to the nearest tenth. So T10 is going to end up being 2.4 kilograms in my case. So therefore, we have 2.4 kilograms left after 10 years, or in 10 years. Okay? So there's an example of just doing a Tn calculation. Okay? With the help of your calculator. Okay? Let's do another example here. I think I've got one more I'm going to do. We're going to do a growth percentage example, and then I'm going to give you 7 or 8 questions to try, and then tomorrow we're going to do part 2. So today we're looking here at, we're in about 20 minutes, so it's going to be about a 30-minute instruction again, and then you can work on practice. Okay, so I think I can fit the last one in here. Okay, so this is the one where you're going to grow a population. So in these types of questions, the common ratio is going to be like greater than 1. So you have to be careful how you write them. All right, so this is an example of growth percentage. Okay, here Robbville, town of Robbville has 260 people. It grows 5% every year. What is the population in 25 years? Okay, when you are growing the population, you're gaining 5% every year. So your R value is not going to be 5%. It's not 5 out of 100, because that would be shrinking. Your R value is going to be 100% plus 5. So you have to keep that in mind. So that's the first thing not to get tricked on when you're growing. When they give you it's growing by 5%. The actual R value is that 100% plus you're gaining 5% more. So this is going to be 105%. Okay, so then you have to convert that into a decimal. So 105 out of 100, which equals 1.05. That is your common ratio. So for example, if I had 100 people, the next year I'd have 105. Okay, and that's how it works. Now, what we also know is that I start off with 260 people in my town here. So I know that my first term is 260 people. And I also know that I have a value here of 25 years going first year, 25 years. So second year, third year, first year we have this, second year we have another one, third year we have another one. So we're going to say that the n value is equal to 25 years. What's going to be after 25 years? Okay, so we can use the formula for that. So we want T25. You have to be careful. Sometimes you might think, well, what is the population in 25 years? Well, in 25 years, I guess, would be, if we think about it, if I just do an example of 3 years. So year T1, T2, and T3. Let's do that. So this is so here's my first year. In 1 year, in 2 years. Okay, so we're actually gaining an extra one here. Okay, so we're actually looking to find out how much is it going to be in 25 years. So we're looking for the 26th term, 25 years after the first term. So you got to be careful with the wording sometimes. Okay, I'm usually not too sticky about that, but the book can be when you're checking your answers. So be careful with that. So we're actually looking in 25 years. So let's write this out so we don't get confused. Let's say that I want in 25 years. So I'm looking for the 26th term of the series. Or sequence, pardon me. It's not a series. That's one of the next area. That's 1.4. Okay, so I'm actually looking 25 years after year 1. Okay, so we know what R is now. We know what the first term is. We know what N is. So let's get T26. That's going to be T1 times R n minus 1. So we're ending up with 25 there, which is what we want, right? Because it's going to be 26 minus 1. So T26 then is equal to 260 times 1.05 to the power of 25, because 26 minus 1. Now we have to do this power stuff before we do the multiplication, otherwise we'll be messed up. So take out your calculator, go 1.05, raise it to the exponent of 25, hit the equal button, and then multiply by 260. Okay, and we're going to round to the nearest person. I get 880.45, so let's say 880 people. Okay, so there are three basic examples of using that general formula. Now there are other kinds of examples. If we look in part 2, I'll just give you a little preview of part 2 here. Tomorrow, next day, we're going to be looking at, let's see here. In day 5, we have about a 25-minute class to 30-minute class again. And we're going to be looking at a few more examples. And we're going to be like finding, rather than finding just the Tn, we're going to be looking at finding maybe T1 or N values. So we have to use different types of calculator work. But that'll be tomorrow. So for today, I'm going to focus on giving you a small practice area for 1.3, and that should be good. So for today, where's my little practice area here? Let me part 1 there. Okay, so you can try. This is on page, where is it here? I got to get to my notes here. Okay, so this is on page number 39. You are going to be looking at doing 1, do ACE, 2 ACE, and all of 3. Okay, so that's not too much. And this is in 1.3 section. Okay, and then tomorrow we'll focus us on some other kinds of examples, calculating N's, calculating T1s. So we'll do 3 or 4 different new examples in that. Okay, again, like always, if you have any questions, feel free to email me if you need to, chat me if you need to, or come see me if you're right here in Vanguard, and I'll help you out when I can with whatever you need. Okay, so that's about, we did pretty good today. Didn't even get to 30 minutes, nice short one, so you should have no trouble finishing up. Okay, we'll see you tomorrow.